6.6 Lewis structures. So we're finally at Lewis structures. These were given to us by Gilbert Lewis, who also gave us Lewis acids and bases. So in a Lewis structure, the dots represent electrons. So what you'll have is a structure that looks something like this. It'll have an element, in this case we've got fluorine, and fluorine is going to share a pair of electrons with a neighboring fluorine. Okay, so these are shared and they form the bond. Then we've got extra electrons on the outside, and these are lone pairs. Or non-bonding pairs. Oops, non-bonding. Okay, notice that every atom, except hydrogen and helium, want 8, and that both of our fluorines have 8 electrons. I'm sure you can see all of them. There we go. So to build these Lewis structures, we're going to need to determine the total number of electrons in compounds. Remember when we looked at our periodic table and we figured out valence? The hydrogen, lithium, sodium, potassium, rubidium, they all have 1 valence electron. Beryllium, magnesium, calcium, strontium, barium have 2 valence electrons. We're going to skip the transition metals, and then we skip right here to boron, aluminum, gallium. They have 3 valence electrons, and we go on across 4, 5, 6, 7, and 8. These are the number of valence electrons. Okay. So our first example is this compound here. It's got 2 hydrogens and 1 sulfur. So we're going to count up our valence electrons. We'll see that hydrogen is in the first row, so it has 1 valence electron. And sulfur is here. It's got 6 valence electrons. Okay. So we have 2 hydrogens. Each one has 1 electron. And then we have sulfur, and we said sulfur had 6 electrons. That gives us 8 electrons. Let's look at iodine. Oops. Iodine is right here, and it has 7 valence electrons. In this compound, because of that subscript, I've got 2 iodine molecules. So I've got 2 times 7 for 14 electrons. Let's look at carbon tetrachloride. Carbon is here. It has 4. The chloride is here. It has 7. So let's count up our electrons. Carbon has 4, and we have 1 carbon. We have 4 of the chlorides. Each chloride has 7, so it's 4 times 7. That's 28 for 32 electrons. And then here we've got a hydroxy. Oxygen. I have to get hydrogen on there too. Oxygen has 6. the hydrogen has 1. This one's got a little addition to it. Oxygen has 6. Hydrogen has 1. And then we've got that little negative charge. Let me get another color. That little negative charge there, that's an electron. And so we'll want to add 1 more for the negative charge to give us 8. So when we draw a Lewis structure, our goal is to give every atom 8 electrons except hydrogen and helium, which only get 2. These are our steps for drawing a Lewis structure. We're going to start with number 2, a little out of order. Determine the total number of valence electrons. We just did that on the video before this one. Determine the arrangement of atoms. We can do that by looking at a periodic table. Generally, this first column will make 1 bond. There's not a pattern for these until we get to carbon. Carbon likes to make 4 bonds. Nitrogen likes to make 3 bonds. Oxygen, sulfur, likes to make 2 bonds. And our halogens like to make 1 bond. So if you're given an atom like a carbon, you're probably going to put a molecule that has a carbon in it, put the carbon in the middle. Try and give oxygen 2 bonds. Stuff like that will help you draw these structures. Okay, so after we've determined the arrangement of the atoms and we know how many valence electrons we have, we attach each atom to a central atom with a pair of electrons. So that's where our first electrons are going to go. We place the remaining electrons using single bonds to form complete octets. If you run short of electrons, consider making double or triple bonds. So let's look at some examples and see how we do this. So let's draw the Lewis structures for these compounds. We know that from our list that hydrogen is only going to make 1 bond. So it can't be in the middle. We've got 3 atoms here, so we can't put the hydrogen in the middle because it only makes 1 bond. So the sulfur will have to be in the middle. And we counted up our electrons last time and we came up with 8 electrons. This is the same molecule where we were counting electrons a little while ago. Okay, so we've got 8 electrons to place. We're then going to have to use a pair here to make a bond between the hydrogen and the sulfur. We'll put a pair here to make another bond between the sulfur and this hydrogen. Now we've got 4 more electrons to place. The hydrogen has 2 electrons, so it doesn't need any more. The sulfur needs 8, and it only has 4. So we can put the electrons here. Now, the ones that are in the double bond get counted twice, because here's the 8 for sulfur, and these 2 get counted also for the hydrogens. And the hydrogen gets 2. So that is a stable, happy molecule. Let's look at the iodine. Iodine, the placement is not a problem here. We just have 2 atoms and they're going to be next to each other. We said that the valence number was 7, so we've got 2 of them. We have 14 electrons to place. We have to put the first 2 here, and then we're going to put the others on the outside. So we've got that gives us 14. 2, 4, 6, 8, 10, 12, 14. Okay, we've got one bonding pair, and this is a lone pair or non-bonding pair. So let's look at the carbon tetrachloride. We've already mentioned that carbon would like to make 4 bonds. So we'll put a carbon, and we're going to put the chlorines then on the outside. Now, how many electrons do we have to place? Carbon has 4. Each of the chlorines has 7. 28. Still 32. Okay, so we have to use pairs of electrons to make the bonds between the carbons and the chloride. So here's 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's 8 of our electrons gone. The carbon has 8 electrons now, so it's happy. We can't put any more on carbon than that. So we'll put these over here. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And that's all of our electrons. Let's look at our hydroxy. I'll move it down just a little bit. Here we have just 2 atoms, so they'll be next to each other. There's no arrangement to go through. The oxygen has 6, the hydrogen has 1, and that charge means I've got 1 more. So I've got 8 electrons. I'll have to do 2 to make the bond between the oxygen and the hydrogen. And then the hydrogen now has 2. We can't put any more on it, but we can put the rest of them here on the oxygen. And now it has 8 electrons, and it's a happy oxygen, and this is a stable molecule. To be officially correct, we should put big brackets around it and a negative sign on the outside, since it is negative. It's a negatively charged ion. Okay, so you've all seen we use double bonds and triple bonds in our Lewis structures if and only if we run out of electrons. Only if you don't have enough electrons are you going to start doing double and triple bonds. So let's look at carbon monoxide. So it's a carbon atom, and it's next to an oxygen, and we don't really have to worry too much about, they're just bonded to each other, so the arrangement isn't a problem. The oxygen has 4 valence, and the carbon has 4, the oxygen has 6, so that gives us 10 electrons to play with. So I'm going to put my 2 bonding electrons in, like that, and then I'm just going to start placing the other 8 wherever I want. I know I want to give everybody an octet, so let's just, that's 6, 7, 8. Well, nobody looks happy in this molecule. The oxygen doesn't have an octet, the carbon doesn't have an octet. 2, 4, 6, oh, I don't have 10 either. Let's give us 10 electrons. But we still don't have an octet. Nobody's happy. Okay, the solution to this problem, I run out of electrons, people don't, then all the atoms don't have an octet, is to erase those that I've just put on the carbon and put them between. And I can erase these that are just on the carbon and put them here. So now I've got 3 pairs of electrons joining the carbon and the oxygen. And I've got this, the carbon has 8, the oxygen has 8 and the carbon has 8. Because the ones in the middle get counted twice, remember? And you'll find that carbon monoxide is written as a triple bond. It's got each one of these lines as a bond, and it's a triple bond. Okay, so let's look at a nitrate ion. It tells us here the nitrogen is central, so we can just go ahead and draw. Okay, nitrogen is going to have 5 plus 3 times each oxygen has 6, and then we've got a negative sign, so I'm going to add one more negative charge. So that's 24 electrons. Okay, we got to have electrons to join ourselves to the nitrogen. So that's 6 right there. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Are we done? Well, we might be. The oxygens all have 8, so they're all quite happy. The nitrogen, though, only has 3. So the solution to this problem is to pick one of the oxygens and remove 2 electrons and put them to make a double bond. Okay? So if you look at this, the nitrogen now has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And each of the oxygens also have 8 electrons. Making those double bonds just makes the electrons go farther. Okay, so let's look at formic acid. We've got the carbon in the middle, it tells us. And then we've got hydrogen, hydrogen, and an oxygen. So the oxygen is going to give us 6 electrons. The carbon gives us 4, and we've got 2 hydrogens that give us each 1. So that's 12 electrons. I'm going to use my erasable. We're going to have a bond between the carbon and the hydrogen, so we got to have 2 electrons there, 2 electrons there, 2 electrons there. That's 6, 7, 8, 9, 10, 11, 12. We've kind of got the same problem. We've got the oxygen is happy because it's got 8. The hydrogen is happy, but the carbon only has 6 electrons, so it's not going to be happy. So we're going to need to remove these 2 and put them here. And that has made a double bond. Okay, there are some exceptions to the octet rule, but you're not to worry about them. You will not be responsible for any of the exceptions that are mentioned.